Hello? Can you hear me?
Yes.
Okay. Well, I'm glad you got here when you did, because I was just about to hang up. You're the only one here, so I didn't think anybody was coming.
Yeah, I'm actually at a my son's game, and I had to do it from a phone.
Yeah. So that's not going to be ideal unless you can see.
Right.
You can't
I
see the
can
screen. You're breaking
hello?
up. I couldn't hear you.
Yeah, I can see the screen.
You can see the screen?
Yeah.
Okay. All right. So what I'll do is I'll go ahead and get into the material, and then I'll share my screen. So give me just a minute.
Okay.
All right. So your classmates definitely have you to thank, because otherwise there wouldn't be a recording. Because I don't make them when nobody shows up. But also, since you're at your son's game, what I'll try to do is move through the material as quickly as possible, if that will be helpful to you.
Yeah, I'm not actually watching the game. I'm sitting down on my phone because my computer wouldn't the data wouldn't work.
Okay. So if you can see here from the screen, we're moving into this week, looking at motion. Last week we focused on the nature of science and measurement, some basic tools that you need to help you in order to understand measurement. So you can see from the screen, we're going to be looking at one-dimensional measurement, one-dimensional motion, I'm sorry, and it's based on measurement concepts that we covered last week, and I'll try to connect that wherever possible. So you see here from the objectives that there are some properties that we're going to be focusing on when we deal with 1D motion. It's the simplest type of motion that we can look at. And so we'll get an idea of some basic concepts regarding motion that you'll use even when we talk about more complicated type motions. Things like position, speed, velocity, acceleration, distance. We'll look at how we can use graphs to help us with motion. And then we'll look at a specific type of motion as well, called free fall motion. So I'm going to go through the notes that I have here in the weekly overviews, and then I'm going to switch to the extra notes that I have that I shared with you last week in the announcements, so that we can look at some example problems once we finish with the basic ideas. So just as a reminder, you do have some assignments that are due this week by Saturday, the 1D motion discussion and problem set number 2. So the 1D motion discussion focuses on the concepts that I'm covering tonight. And you'll do the problem set for that. The problem set for 1D motion won't be due until next Saturday. The problem set number 2 that you see linked here actually deals with measurement and unit conversions that we covered last week. So just to kind of remind you that each week you have a discussion that deals with the current topic and a problem set that deals with the prior week's topic, so that you've had a chance to like review your notes or try some practice, and then or reach out to me with questions before you have to do the actual problem set, which is kind of like homework. Okay. So for this week, there are some notes and videos available to you. The chapter 3 in the textbook that I've linked here deals with 1D motion. There are some 1D motion and free fall videos that relate to the topic that you should check out. What I'm gonna, and also some motion graph. The motion graph videos are also very helpful, so you should take a look at those. Okay. What I'm gonna do is cover the information in my supplemental notes, and then go to the announcements and pull the extra notes so that we can look at some additional practice problems. Okay. Well, I should say additional concepts and practice problems. Okay. So if you see here the objectives listed, and instead of saying 1D motion, you see the word kinematics. So that's a very special kind of word that we use in physics, and it means motion, but more specifically, it means motion without respect to cause. In other words, pure motion. We just want to be able to describe quantitatively a moving object, and we don't care what made the object move. In other words, we don't care about the cause for the object's motion. We just want to be able to describe that motion. And you can see from the objectives, when we want to describe a moving object using kinematics, we focus on things like position, speed, velocity, acceleration, distance, and we can look at a specific type of motion called free fall. And that's because they're all examples of 1D motion, this free fall motion that we're going to talk about. But keep in the back of your mind, things like force that students typically want to bring in at this stage is not relevant, because we're not worried about force, which is causing motion. We're worried about a strictly kinematics representation or description. So pure motion. So that's what they're telling you here. The word kinematics means motion. And so we study motion without its causes. So for example, if we see a group of birds in flight, they're moving, but we would focus on things like, like they mentioned here, how it rises or descends. We might talk about speed, or how fast they're moving, or how far they've traveled, but we don't focus on things like lift, or how the wind might affect their motion, or gravity, because those are examples of forces. And when you talk about forces, you're not dealing with things from a kinematics perspective. So pure motion without respect to cause. Now it mentions here that we do live in a 3-dimensional world. I mean, if you want to describe things in the real world, we have to use 3 dimensions. But if y'all recall from last week, one of the things we said is that we always want to simplify things. We want to model things in the simplest way possible. So in this scenario, to simplify things, we're going to focus only on 1 dimension to get us started. So they mentioned here, for example, a train traveling on a long straight railway is an example of 1-dimensional motion, since it can only move backwards or forwards. Okay, and there's more to this whole describing an object in motion, but we won't add some of those concepts until next week. Okay, so we're just going to be looking at this from a very simple perspective. Right? So these are some examples of some parameters. That word parameters, you can kind of relate it to what we talked about last week, property or quantity. If you recall last week, we said that a property or a quantity is something that can be measured. And so parameter is another way of saying that. And so there are parameters that we can express quantitatively when we want to deal with kinematics, as I mentioned, position, displacement, time, velocity, acceleration. And we'll take a look at those, and we'll learn how to solve problems with those as well. Of course, because some of this is like a terminology thing, we have to get comfortable with the terminology and the definitions of these properties, because you know, with anything, you have to be sure you're using it correctly, and they mean very different things. Okay, so another thing we need to get comfortable with is that because we are trying to quantitatively express these things, we do rely on math. And so you can see here listed on the screen, it says a change in parameter is often represented by the Greek letter delta. So that's some more terminology right there. This symbol delta, the Greek letter delta, is important to us when we're dealing with kinematics because it helps us to express change. Inevitably, if a thing is moving, something's changing. And so that's very helpful to us to be able to borrow from the Greeks and the mathematicians to have a way to mathematically express this idea of change. And so they give you an example. For instance, a change in time, we use the symbol T to represent time. But if we want to say that time is changing, we put delta T. So the delta in front of a variable lets us know that that's the thing that's changing. Okay. Another important thing that we need to keep in mind if we're going to describe a moving object is, well, if we're going to describe an object's motion, well, first of all, we have to be able to locate it. Okay. We have to be able to say where it's at. And then if, you know, and then obviously, if we want to describe motion, then we have to be able to describe, you know, how where it's at is changing. But we have to have a consistent and stable way of doing that, because if we're talking about an object being in motion, we have to say, well, where are you measuring from? How are you establishing the object's position, right? And so we do that within what we call a reference frame, okay? And so it's just it's a convenience to us, depending upon how we choose it, but it's just a way of helping us to locate or give position for an object, okay? So I always like to give the example. So just imagine if you know, where you're at right now, you're sitting, watching your phone or your computer screen, and the question is then, are you moving? And you might be tempted at first, you know, at a first response to say, no, I'm not moving. I'm sitting still, you know, in my room, in my house, in my car, outside. But the truth of the matter is, it really depends on where we're measuring from. With respect to Earth, no, you're not moving. You're stationary at one position on Earth. But if I were on the moon looking down at you on planet Earth, I would see that, in fact, you are moving. Your position is changing. Okay, so where we measure from, what is our reference frame or starting point matters. Okay, and we do have some convenient ways that we do that. For one-dimensional motion, choosing our reference frame with a number line, for example, where we put the 0 on the number line as our start point is a convenience. Okay. So we can use that as a way to represent things. And they're giving you an example here about reference frame. Okay. So they say, you know, for this airplane, we're choosing the Earth as our reference frame. So if you're standing on Earth looking at the airplane, you can see that it's moving. But if you're on the airplane, so with respect to the airplane, if you're on the airplane, you're not in motion, right? Yeah, you may, if you're looking down at the ground, detect motion, but from within the airplane itself, then, you know, you will say with respect to the airplane, you're not moving, and so you can see from that a simple example that it depends on where are you measuring from? What is your reference frame? So you see, we have to have some notation and common understanding when it comes to the properties that we measure, the symbols that we use, and the reference frame that we use to make our measurements. So we'll talk about this property displacement. There's something built into displacement that I don't want to get into too deeply at this point until next week, but just, you know, for the sake of completeness and explaining to you the difference between displacement and distance, I'll go into the example. Okay, so displacement requires that you're tracking an object's position, and in order to do that, you need to know where did the object start from and where is it in reference to where it started. So this displacement looks at how an object's position changes. Okay, it was here, now it's there. What is the difference in its position? How has the position changed? Distance, on the other hand, just looks at the total length that the object has moved. Okay, the total length. So you follow the object around and measure how far it's going. Okay, displacement, you look at where it started and where it stopped. Distance, how far did it go? Okay, and so the simple example that they give here can highlight the difference between the two. So if somebody goes from home to the store, that distance, if they went from home to the store, is 3 kilometers. Okay. Now, in that situation, if the object is just moving in a straight line, moving in one direction in a straight line, the distance and displacement will have the same value. But for example, if we say that the person went from home to the store and back, the distance they travel is 6 kilometers, whereas the displacement is 0. Why? Because they start and stop at the same position. Okay, so that simple example highlights the difference between distance, which is simply how far, and displacement. What is the difference between where you started and where you stopped? Okay. So when we want to quantify displacement, move beyond just the concept of displacement. When we actually want to quantify it, we do delta X, the change in position. X is position, delta X is change in position. How do you determine that? By taking the final position minus the starting position. Okay. There's something else going on with this displacement, but I'm not going to get into it too deeply. So from right now, for our purposes right now, displacement is take the final position minus the starting position. In that formula, delta X equals XF, that F stands for final, minus X, we say naught, the 0 subscript naught. So the difference between where you stopped and where you started. Okay. So they give the example here. If an object moves from an initial position of 2 to the final position of 7 in a reference frame, then its displacement is 7 minus 2, or 5. What about the reverse situation, where the object moves from a position 7 down to position 2? That's why I said a number line is really good to visualize this. In this case, since we say final minus start, 2 minus 7, or -5, okay? Now they talk about the displacement has magnitude and direction. We're gonna save that discussion for next week. You just from this, all we care about is how do we find displacement, take the final position minus the starting position as if we were on a number line. We'll complicate things by talking about direction next week, okay? The unit for displacement in the metric system, which recall last week I told you that's primarily what we use, the metric system. So the unit for displacement is the meter, but also its counterpart distance is also measured in meters. Okay, so you can't just look at the unit to determine whether you're dealing with displacement or distance, because they both use the same unit. What you have to understand is what is fundamentally the difference between distance and displacement. Distance looks at how far you went, the whole entire path. Displacement looks at the difference between where you stopped and where you started. We're not going to go into scalars and vectors. That's next week. Okay. So as I mentioned, you need a coordinate system or a reference frame. And typically when we're dealing with one-dimensional motion horizontal, we use a horizontal line. That's like the number line, okay? Where the middle is 0, right to the right is positive and to the left is negative, okay? So that's our reference frame. We could also take that same line and do vertical. We could turn it vertical. And in that particular case, the middle is still 0, but up is positive and down is negative, okay? And we'll get deeper into this whole direction business next week. You just need to ask yourself, hey, if I'm looking at horizontal motion, then I'm gonna use a horizontal number line. If I'm looking at vertical motion, I'm gonna use a vertical number line, okay? Time. So inevitably, if an object is moving, time is a factor because time is changing. I mean, that's the reality, right? Time is always changing. So we have to have a way of talking about how much time is elapsed between events, okay? How much time did it take the object to go from position A to position B, all right? We use the unit seconds when we're dealing with time. Remember, in the SI or metric system, the unit for time is the second. And if we want to talk about elapsed or how did time change, we find delta T. So delta T is the final time minus the initial time. Okay, and here they say the beginning time. So final time minus starting time. Final time minus initial time. Okay, all those terms really mean the same thing. What you're finding is the time difference. Okay, and they tell you about, a lot of times it's convenient to set your starting time as 0. Imagine if you were gonna, monitor a race, you would have a stopwatch, and when the race starts, your stopwatch would be on 0, and then you would, measure, how much time it actually took from your starting time, right? Delta T in this case would be just T. A lot of times, if we set the starting time, for our clock or watch or whatever to be at 0, then delta T is simply T, okay? We don't need to distinguish T final because, well, I mean, if T initial or the beginning time is 0, then there's no value in having a subscript because all you're measuring is the final time. Average velocity and speed, okay? So average velocity is defined as the displacement divided by the elapsed time. Now, truthfully, if you want to be complete about this definition about average velocity, So they're using that V with the little bar over it to represent average velocity, okay? Really, it should be delta X over delta T. In this definition that you see in the brown looking box, they assumed that the starting time was 0. But if you want it to be complete, you would say that average velocity is equal to delta X over delta T, okay? We don't need to, we're not gonna focus on the fact that it's a vector at this moment, because we'll talk about that next week. What we wanna focus on here is that there's a difference between average velocity and average speed. Average speed looks at the distance traveled over the elapsed time. So distance traveled over the time it took to go that distance, okay? We will see next week that average velocity and average speed are very different, okay? Just go back to the example where they went from home to the store and back. Well, they went from home to the store and back, and their distance was 6 meters. We don't know how much time it took, but whatever it was, if we're going to get average speed, it'd be 6 meters divided by whatever time. On the other hand, because they stopped and started at the same position, the displacement was 0, so the average velocity would be 0, okay? So just in that little simple example, you can see there's a difference between average velocity and average speed. But next week, we're going to focus on an example that'll really clarify the difference between the two, okay? Now, the thing is that we use the unit meters per second for both of them. Velocity and speed are both in meters per second. So one thing that you should see from all of this is that you can't always look at the unit to figure out whether you're dealing with velocity or speed. You have to be careful with that. You have to know the definition and the difference between the two. All right, they're both measured in meters per second, but they don't mean the same thing. They're just, they use the same unit though. Instantaneous velocity and speed. So average velocity and speed are different from instantaneous velocity and speed. What you can see kind of like is average speed is looking at the trip that the object makes or takes as a whole. But instantaneous velocity and speed is looking at one particular moment during the trip at an instant, okay? So instantaneous velocity, the velocity at a specific moment, not for the whole trip, at a specific time during the trip, okay? And so, you know, really and truthfully, to find the instantaneous velocity, you need a little bit calculus, but we don't really get into that. So anytime you have to use instantaneous velocity, I have to give it to you, okay? And typically typically any velocity that you're given is an instantaneous velocity. If I want you to find average velocity, I'll be specific about that. But if you're told that an object has a velocity of 5 meters per second, they're talking about instantaneous velocity, unless they specifically say average velocity, okay? Instantaneous speed. So it is how fast an object is moving at a particular moment. You can think of it that way, okay? Typically when we say how fast, we're talking about speed. Just like if you're looking at your speed gauge in your car, it tells you how fast you're going. Or just imagine that you're looking at how fast you're going at a particular moment. It's like what the cop does you with the radar gun, right? Gotcha. That was your speed at that moment that I clocked you, okay? Both of these, instantaneous velocity and instantaneous speed, also use meters per second as the unit. So you got 4 different things that you can measure for a moving object, and all 4 of them, average velocity, average speed, instantaneous velocity, instantaneous speed, they all use meters per second, okay? So you see that unit business is very critical. Acceleration. So the acceleration of an object, how the velocity change per unit time, not how the speed change per unit time, how the velocity change per unit time, okay? You can produce an acceleration by changing an object's speed, but you can also produce an acceleration by changing an object's direction. Or you can do both. So when you produce an acceleration in a car, you can hit the brakes, you can hit the gas, or you can steer the wheel. All of those produce acceleration because all of those contribute to a change in velocity, okay? All right. We don't get too much into, this idea of average acceleration versus instantaneous acceleration. We don't really have to deal with that in here. What you do need to understand about acceleration in terms of units is that in the metric system, the unit for acceleration is meters per second squared. Meters per second squared. That's an important unit because that's the one that gets butchered the most in this class, okay? So acceleration looks at how an object's velocity changes per unit time. You can produce acceleration by changing the speed or direction or both. Speed up, slow down, steer the wheel. And the unit is meters per second squared. Okay. Now they talk about here, they talk about the idea of acceleration versus deceleration. I'm not going to go into all the different permutations. We're going to keep it simple here. For us, when an object is accelerating, okay, it could either be, when we talk about acceleration, I don't like to use the word deceleration, right? I just like to say that the acceleration of the object is positive or negative. Acceleration can be positive or negative. Don't use the word deceleration. Get into the habit of saying acceleration can be positive or negative. Now, for us to keep it simple, when the acceleration is positive, the object is speeding up. When the acceleration is negative, the object is slowing down. When the object is speeding up, the velocity is getting bigger, it's going faster, it's speeding up. When the acceleration is negative, the velocity is getting smaller, the object is slowing down, okay? So just keep that in mind. We want to keep it simple. Hit the brakes, hit the gas, hit the brakes, steer the wheel. Hit the gas, speed up, acceleration is positive. Hit the brakes, slow down, the acceleration is negative, okay? Constant acceleration. So the reason we don't have to focus on this idea of instantaneous or average acceleration is because we're gonna, the kinds of motion we wanna really zoom in on deal with constant acceleration, okay? So we wanna focus on motion where the acceleration is constant. Please do not mix up acceleration and velocity. Constant acceleration means the object is either speeding up or slowing down uniformly. Constant velocity means the object is not accelerating at all. So if you don't know the difference between those two, you mix up those two variables, and students do that a lot, okay? So please pay attention. Constant acceleration, think about it from a perspective of hitting the gas or the brakes. Constant acceleration means you're always speeding up or always slowing down. Constant velocity means you are not accelerating, okay? So there are some situations where we can look at motion as having constant acceleration. and that helps to simplify things, okay? When we're gonna see some equations that we can use when an object has constant acceleration. Because remember, our goal is to quantitatively describe this moving thing. Well, if the object is obeying constant acceleration, there's a set of equations that will automatically do that for us, okay? And we're gonna take a look at them. An example of motion where an object is moving with constant acceleration is free fall. When an object is being controlled by gravity only, vertical motion, under the control of gravity only, is an example of free fall 1D motion, okay? So here are the equations that will help us to describe an object that is moving under constant acceleration. So if an object is moving under constant acceleration, these equations that you see here on the screen are what we need. That's all we need. If the object has a constant acceleration, if A is constant and it's not changing, notice if A is constant, all those other things can change. But if A is constant, it is not changing. And so we can use the equations that you see there to describe a moving object. Now, we will see in the example problems that I solved for you. I'm not trying to make things too complicated for you in terms of using these equations. The kinds of problems that I'm going to ask you to solve are going to be even simpler than what these equations allow you to do, okay? So I'm gonna take these equations and water them down even more, make them even more basic so that you can, you know, so that you can solve simple problems relating to 1D motion. What about when the object is falling? As I mentioned, free fall is an example of 1D motion in the vertical direction, and this constant acceleration because gravity is constant. Gravity controls the vertical motion of an object. And when gravity is the only thing controlling the motion of the vertical motion of an object, and we call it free fall. And in that instance, we can go back to these equations, and everywhere there's an A, we can put in G. We just have to remember, everywhere we have an A, put in a G, but we have to remember, because gravity points downward, that I like to always say, replace A by minus G. And then that'll make your life, that'll make everything complete so that you don't forget the minus signs, because we say gravity pulls objects down. And so we're replacing A with G, but we have to remember to replace, you know, put minus signs in the appropriate places, and you'll see that in just a moment. Also, when we're dealing with vertical motion, we use Y instead of X. We use X to represent horizontal motion and Y to represent vertical motion. Okay. We can also use graphs to help us analyze motion. And we'll see some examples of that when I go into the extra notes that I have. So we can analyze or describe motion using equations, or we can describe or analyze motion using graphs, and we'll see what's the connection between the equations and the graphs, okay? All right. So those are my supplemental notes. I would highly encourage you to look at the 1D motion videos, the free fall motion videos, and the motion graphs. Those are great visual explanations of the things that I've just covered in my notes, okay? So what I'm gonna do now is I'm gonna go into the announcements. And if you didn't see this last week, I'll just kind of remind you that there are extra videos on all the topics that I cover. You see here, there's extra videos on these topics here. 1D motion that I'm covering this week, vectors and 2D motion that are coming up. And there's a listing of the class videos from class meetings. So there's videos from last week and the week before. And then extra resources. Recall, these are some extra notes that I made available to you. And so if you click, you'll see that there's a folder on every topic that we cover, okay? And so since this week we're 1D motion, that's what I want to go into. And we'll take a look at some examples, okay? All right, so I'll go through these items that I have there for you. So in this particular slide, if you recall, I told you that the unit for acceleration is meters per second squared. So I show you how you get that unit using the idea that acceleration is change in velocity per unit time. Change in velocity means what? Final velocity minus starting velocity. And then time, okay, assuming that the starting time was 0. Okay, so how does that break down? Well, VF minus VI, final velocity minus initial velocity, gives you meters per second. And then you're dividing that by time, which is in seconds. So when you resolve that, meters per second over seconds, I treated the seconds in the denominator like a fraction. So when I divide by a fraction, I multiply by its reciprocal. So that becomes meters per second times 1 over second, which resolves to meters per second squared. So how do you get the unit for acceleration? This shows you. Do I expect you to go through all of this every time you solve a problem? No. If you know that you're finding acceleration, you know that your unit must be meters per second squared. But if you need to do this multiple times to convince yourself that you understand, then do it. The other thing I have here is just, this is a nice visual to help you understand free fall, okay? So it defines free fall for you. Free fall is vertical up and down motion under the influence of gravity only. And so on planet Earth, gravity causes an object to accelerate downward at a rate A equals G, 9.8 meters per second squared, during free fall. No air resistance. So anytime an object is free falling, anywhere on planet Earth, if it's free falling, gravity only, you automatically know the acceleration is 9.8 meters per second squared, downward, okay? So I make the connection here between general accelerated motion, which uses A, okay? So the change in velocity per unit time, where you have constant acceleration. And then if you take this and transform it to represent vertical motion, you still have VF minus VI, you still have T. But the difference is that in the place of A, I now have G. Because if it's free fall, gravity is in control, and gravity is always 9.8 meters per second squared down on planet Earth. If you're dealing with general accelerated motion, then they might give you A, or you might be tasked to find A. But if you're dealing with free fall motion, you will never have to solve for the acceleration. Why? Because the acceleration is given as G, 9.8 meters per second squared down. Okay, so when you're dealing with free fall, think about it. Any kind of vertical motion under the control of gravity only, we know the acceleration, G, 9.8 meters per second squared. Well, what if I drop the object? Well, dropping it just means that the initial velocity starts from 0, but the acceleration is 9.8 meters per second squared, G, what if I pitch it down or throw it straight up? Pitch it straight down or throw it straight up. Well, that just means the starting velocity is not 0, but the acceleration is always 9.8 meters per second squared. This is where students get into trouble because they think pitching it up, throwing it down, you're exerting more force. So that's not going to be free fall. No, the moment it leaves your hand and gravity takes over, no air resistance, that's free fall. Meaning what? The acceleration is always 9.8 meters per second squared. Okay. So if you're reading a problem and it says an object is in free fall or object is dropped or is thrown straight up or thrown straight down, then you automatically know the acceleration. Okay. Doesn't matter how tall a building is. Doesn't matter how much time it spends in the air. If it's free falling, the acceleration is 9.8 meters per second squared. Now you might still have to find VF or VI or T, but you won't have to find A if it's free fall. I think this is just a duplicate. Yeah, it's just a duplicate of the whiteboard there. All right. And I'll come back to that one. I want to go into this one first because it has some nice examples in it. Okay. So this is just another set of notes and some sample problems dealing with motion. So they talk about speed, velocity, acceleration. And this, in this packet, it actually gives you the level of problem solving that I expect you to do and the level of problem solving that you'll see in problem set number 3, part B. Okay. So I talked about the idea of needing a reference point. And the reference point is the fixed point that you measure from to establish motion, to locate an object, to find its position. Okay. And so if an object is in motion, that means its position is changing. So you establish the reference point and the object changes its position with respect to that reference point, then you know it's in motion. Okay. So this is a nice little kind of tongue-in-cheek example. It says you're a passenger in a car stopped at a stop sign. Out of the corner of your eye, you notice a tree on the side of the road begin to move forward. Well, you know, let's hope that there's nothing really going wrong with you so that you believe that the trees are actually moving. I mean, you know, this is not the Lord of the Rings. It means that you've mixed up the reference point, right? Because the tree, which is fixed, is the actual reference point, and you are moving with respect to that, okay? So be careful, because how you interpret the reference point will influence the measurements that you make to establish motion and determine the properties that we want to know about a moving object. Speed, here's a nice definition of speed, and I love that they gave you the pyramid. Speed is the rate of motion. So rate means that time is involved. And in this particular case, we're looking at the rate of motion or the distance traveled per unit time. Speed, distance per unit time. So in the pyramid, they're using that V to represent speed. And then you have D for distance and T for time. So if you're looking for speed, this is the pyramid that you need, right? Distance per unit time. You can have instantaneous speed, recall speed at a given moment. That's not something you would be calculating. You would have to be given instantaneous speed. And most of the time, if you're given a value for speed, if they don't specify that is average, they're talking about instantaneous. But how do you find average speed? Total distance over total time. So remember, average looks at the total or the whole trip. Instantaneous looks at one moment during the trip. So let's talk about the difference between speed and velocity. Even though I've highlighted it, I'll state it again. with this simple example. Says a storm is 10 kilometers away and is moving at a speed of 60 kilometers per hour. Should you be worried? Well, it depends. Is the storm coming straight at you, or is it going away from you? If it's going away from you, of course, you're praying for your neighbors, but you're not as panicked. So direction matters. So this emphasizes a very key point that when we're describing a moving object, there are some properties that involve direction. Speed is not one of them. Speed does not involve direction. Speed involves distance and time. But its counterpart, velocity, involves direction. So speed plus direction. You can kind of think of velocity as speed plus direction, okay? And we'll get into this direction business deeper next week. For this week, when you find velocity, if you do it correctly, the direction is built in, okay? And so this idea that velocity can change even when the speed is constant. So put your car on cruise control, speed is constant. But if you turn a corner or drive around in a circle as they are, the one thing that's changing is direction. So speed is fixed, but direction is changing. Remember, for velocity, if you change the speed or the direction, then the velocity changes. Hit the gas, hit the brakes, steer the wheel. If you do any of those, you change the velocity and produce an acceleration, okay? Acceleration. So here is the definition of acceleration: the rate of change of velocity. The rate of change of velocity. So the change in velocity per unit time, okay? When we want to talk about how the velocity changes, we look at the final velocity minus the initial velocity divided by the time. That will give us acceleration. VF minus VI divided by T. And so you can see in the pyramid, VF and VI come together. They're grouped together, okay? And then you have on the bottom, A and T. So remember, when you use a pyramid, whatever you're looking for is the thing you cover up, and then you use the other items to help you find it, okay? And we'll see that here shortly. So as I said, we're going to keep it simple. Positive acceleration, speeding up, hit the gas. Negative acceleration. Acceleration can be negative when you're slowing down, hit the brakes. Do not say decelerate. Positive acceleration, speeding up, hit the gas. Negative acceleration, slowing down, hit the brakes. And you know inherently, if you're speeding up, your velocity is getting bigger. If you're slowing down, your velocity is getting smaller. All right? So let's look at a couple of sample calculations here. So it says your neighbor skates at a speed of 4 meters per second. You can skate 100 meters in 20 seconds. Who skates faster? So in this particular case, because we're looking at speed, we need to know who has the bigger speed, because that will tell us who is going faster. Well, I know the neighbor's speed, they gave it to me, but the question is, what is my speed? Well, in order to find speed, I need distance and time. You can see in the given column, they gave me the distance and time. So I divide, because D over T, you know, when you look at the pyramid, if there's one on top of the other, you know you're dividing, right? You're dividing D by T in this case. So 100 meters divided by 20 seconds in the work column, 5 meters per second. So my speed is bigger than the neighbor's speed. So I skate faster, or you skate faster, okay? But we had to find speed in order to answer the question, okay? I can't just look at that and say, oh, I skate faster. I have to show the work, okay? That's one of the things you need to get accustomed to in this class is having the right answer does not always mean you're going to get the credit. If you didn't show the work when there was work to be shown, you won't get the credit. Show me, okay? And also be careful that when you're asked a question, you answer the question. To work this out and get V equals 5 meters per second and then stop would not answer the question, because the question was who skates faster? If you don't answer that, then you did not fully address the question, okay? So I always like to tell students, you have to show the work, but you also have to use that work to answer the question. Okay. Says here, a roller coaster starts down a hill at 10 meters per second. 3 seconds later, its speed is 32 meters per second. What is the roller coaster's acceleration? Well, just from the way to describe the problem, we know that what's happening with this roller coaster is you know, you're on one of those roller coasters where it's zooming down the hill and it's getting faster, okay? Speeding up. So if it's speeding up, it means it has an acceleration. And if it's speeding up, it means that acceleration has to be positive, okay? See, this is where the concepts will come in to help you problem solve, because if you understand that speeding up means the acceleration is positive, then you will approach it when you solve this problem the correct way, okay? So they gave us the starting velocity, 10 meters per second. They gave us the final velocity, 32 meters per second. They also gave us the time because they said 3 seconds later. That means what? The clock moved forward 3 seconds. So I know my time, okay? So to solve for A here, cover up the A in the pyramid, tells me I got to do VF minus VI together and then divide that by T. That's what the parentheses on VF minus VI tell you, that they're grouped together, right? Because you know, if you do an order operation, right, you do parentheses first. Okay, that please excuse my dead Aunt Sally, or however you say that, right? Dear Aunt Sally, dead Aunt Sally, however you want to call it, you have to use the proper order of operation. So we do 32 meters per second minus 10 meters per second first. That gives me 22 meters per second. And then I divide that by 3 seconds. So 22 divided by 3, that's 7.3. And then meters per second divided by second. Well, that's what I just showed you in terms of how the units work out. I know that that's going to give me meters per second squared, because that's the unit that goes with acceleration, okay? So you have to have your number correct and the unit correct in order for it to be correct, and you have to show your work. So let's take a look at this example. It said, sound travels 330 meters per second. If a lightning bolt strikes the ground 1 kilometer away from you, how long will it take for you to hear it? Now be careful, because a lot of students read this, how long, and then they just start working. Because how long, just those 2 words alone, how long means a distance. But how long will it take? Those words put together imply that we're looking for a time, okay? All right, so in this particular case, they've given us the speed that's involved, 330 meters per second. That's how fast sound is moving. And then in this particular case, you know, you see the lightning strike and it's 1 kilometer away from you. And then the question is, how long does it take before you hear the thunder, right? Okay. So speed is 330 meters per second. They gave me a distance of 1 kilometer. I have to convert that to meters. Why? Because my speed is using meters per second. If my speed was using kilometers per second, then I could leave my distance in kilometers. But I have to always remember that I need like units so that I can cancel, okay? So if I go back to my distance, speed, and time pyramid, If I want to find the time, I have to take the distance and divide by the speed. So that becomes 1,000 meters divided by 330 meters per second. My meters cancel out. I have meters on the top and meters on the bottom, so they're going to cancel. Do the number part, 1,000 divided by 330. All right, that gives me 3.03. And then once the meters cancel, all I'm left with is seconds. Okay. And of course, I know if I'm finding time, what should my unit be? Seconds. All right. So see, I tell students all the time, when you're problem solving, if you go back to these pyramids and you keep the units in mind, you're going to be okay. But a lot of students like to abandon the pyramids and go to using equations. If you're comfortable with that and you know what you're doing, fine. But if you're, like in the beginning stages of this whole problem solving business, please try the pyramids, because you will be able to fill in the things that you know, and then the thing that you're looking for will be a simple multiply or divide. Okay. Says, how long will it take a car traveling 30 meters per second to come to a stop if its acceleration is -3 meters per second squared? Well, I know what's happening to this car. Somebody hit the brakes and the car is slowing down. So my acceleration has to be -3 meters per second squared. Okay. So the car was going 30 meters per second. It slows down to a stop. How much is it its velocity or speed if it comes to a stop? 0, right? So I know my starting velocity, 30 meters per second. I know my final velocity, 0 meters per second. I know my acceleration, -3 meters per second squared. So now, what am I looking for in this pyramid? Time, because they say what? How long will it take? Okay, so I'm looking for time. So now I can take my pyramid and plug in the things that I know. I know my final velocity is 0. Please be careful with that, because a lot of students take the 30 meters per second and they put it in place in the wrong place. They put it in front because they think, well, if I'm subtracting, I have to put the bigger number in front. No, the formula says VF. So whatever VF is what goes in the front. Okay. In this case, since I'm stopping, my VF is 0 meters per second minus my starting velocity, 30 meters per second. So when I do that subtraction, I get -30 meters per second. So a lot of students want to always make sure that that subtraction comes out positive. That is wrong. And you know that is wrong because if you're slowing down, it means your velocity is getting smaller. So you have to get a negative value there. You're decelerating, slowing down, hitting the brakes, okay? So -30 meters per second. And then you're going to divide that by -3 meters per second squared. Well, if you go back to the rules for integers, negative divided by negative gives me positive. 30 divided by 3, that's 10, okay? And then meters per second divided by meters per second squared. Well, what you have to think about is you have meters per second on the top and you have a meters per second on the bottom that are going to cancel. And the only thing you're going to be left with is seconds. But if you know the unit that you're looking for, then you don't have to worry about all that. You know that the unit that you're supposed to get is seconds. Why? Because you're measuring time, okay? That's why I said that it's very important that you understand the property that you're dealing with and the unit that goes with it, so that when you problem solve, you get the correct unit, okay? Because if you tell me 10, but then you give me a unit of meters per second or meters per second squared, that's wrong, because time can't be measured in meters per second or meters per second squared. Time is only measured, for our purposes, according to this problem, in seconds, okay? Units matter. All right. So I encourage you to go back to the weekly overview and watch the video that deals with graphing, because they explain some really good properties and give some really good examples on that. But what I want to do here is just to highlight some basics, some basic types of graphs, and some basic information that you can get from graphs. Because remember, we can describe our moving object using equations, just like we just did in the 3 or 4 examples that I showed, or we can use graphs, okay? But when we look at the graphs, we have to decide first, what type of graph is it? And then based on the type of graph that it is, what kind of information can I get from it, okay? So the first type of graph that I want to look at is a distance versus time graph. Distance versus time. I know that it's a distance versus time graph because I have distance on the vertical and time on the horizontal. Those of you who have me for lab class, in lab, you talk about the idea of an independent variable being on the vertical, in this case, distance, and the independent variable being on the horizontal, in this case, time, okay? And so when you look at a distance versus time graph, notice I did not say a time versus distance. I said distance versus time, because when you read a graph, you always read the vertical first and then the horizontal second. So distance time graph, or distance versus time graph, okay? So when you look at a distance versus time graph, the slope of the graph, the steepness, tells you about the speed. Well, we have 2 objects moving here, object A and B, and I know that because I have 2 very different lines on this graph, okay? I can look at this and say that I know that object A had a faster speed because it has a steeper slope. Steepness, imagine if I had to hike up line A versus hike on line B. Okay, the hike on line A is going to be a much steeper hike, much more challenging than to hike on B, because A is much steeper than B. But when you look at it from a distance time perspective, that steepness tells you about slope, which tells you about the speed, faster speed, steeper slope, faster speed. So A is going faster. I know that. If the line is straight as in not flat, but straight as in, like A is totally straight, but B is not, okay? So this straight line, like A, tells me that that object had a constant speed. Object B didn't have a constant speed because the line is not totally straight. When I see a flat line, now you see on object B, there is a portion of the line that is flat. Well, during that portion, during that time, from, in this particular case, it looks like it's 10 minutes to 20 minutes, the line is flat. That means the object wasn't moving, there was no motion. So you can see just by looking at these 2, object A was always in motion for the whole time. Object B had a period of time where it wasn't in motion. You see, just by looking at the graph, I can tell you that object A moved faster, object B stopped for a moment, for a time period. Object A had a constant speed, object B did not, okay? So that's the kind of stuff you need to be able to look at a distance time graph and answer and understand and use to help you describe a moving object. So that's what the questions ask about the graph here. Who started out faster? Well, obviously object A, because it had a steeper slope. And who had a constant speed? Object A, because the line is straight. And what happened to B between 10 and 20 minutes? It stopped moving. Why? Because the line went flat. And then we can do some computations when we look at a distance versus time graph. See, a distance versus time graph allows you to find average speed. Average speed, okay? In other words, well, I mean, that's what we would focus on when we look at a distance versus time graph. Average speed. Average means what? Look at the whole trip. So for object A, over the whole trip, it covered a distance of 2,400 meters. And it took a time of 30 minutes. So 2,400 meters divided by 30 minutes, 80 meters per minute. Object B, on the other hand, it went for the same 30 minutes, but it only covered 1,200 meters. 1,200 meters over 30 minutes, 40 meters per minute. So in fact, what we said was that what? Object A was moving faster, which proves to be true, okay? And we figured that out by looking at the average speed, which we could calculate from a distance versus time graph, all right? What if you have a distance versus time graph that looks like this? You see, there's no straight lines on here, okay? Now, while I don't expect that you will calculate slope on here, one thing that we do know by looking at this distance versus time graph, since it's a curve, the object was accelerating. So anytime you look at a distance time graph and it's a curve, then the object was accelerating. Okay. So I don't know all the particulars of the motion for this object, for example, like the velocity, but I do know that the object was accelerating, which means its velocity was changing. Okay. In other words, I might not be calculating the exact amount of the velocity change, but I do know that it was changing because this object is accelerating. All right. What if we look at a speed versus time graph? Speed versus time graph. Okay. When you look at a speed versus time graph, the slope relates to the acceleration. So positive slope means the object is speeding up, meaning your acceleration is positive. Negative slope means the object is slowing down or your acceleration is negative. A straight line means the object maintains a constant acceleration. And then a flat line, no acceleration, constant velocity. So straight line means the acceleration is constant. Flat line means the velocity is constant. Okay, that's why, see, it's really important that you understand the distinction between velocity and acceleration. Okay. So let's look at this example graph here. So this is a speed versus time graph. And just by looking at this graph, I can tell you certain things. So when was the object slowing down? That means that the slope is negative. So decreasing from left to right. So if I look at this graph, when was the slope of the line decreasing left to right? Between 5 seconds and 10 seconds. Okay. When was the object speeding up? Speeding up means the slope is positive, increasing from left to right. So between 0 and 3 seconds. Now, truthfully, if we analyze that even deeper, we can say that the slope from 0 to 2 seconds is different from the slope from 2 to 3 seconds, right? You can see that from 2 to 3 seconds, the slope is much steeper. So, you know, it was speeding up by a bigger amount, or the acceleration was bigger between 2 and 3 seconds than it was between 0 and 2, but it still was speeding up. Okay. When was it moving at a constant speed? Remember, flat line means constant speed. So between 3 and 5 seconds on this graph, the line is flat. That means that the speed is constant. And if speed is constant, you're not speeding up or slowing down. It's staying the same. So no acceleration there. And then not moving. Oh, okay. So, you know, if it's not moving means the speed is 0. Well, where on this graph is the speed 0? At the start and at the finish, at 0 seconds and at 10 seconds. Okay. So you see, I was able to tell some things about the motion of whatever this object is just by looking at the graph, right? I didn't have to have any equations, and I could still describe what's basically happening to this object. So remember, I can use my equations, you know, my problem solving pyramids with speed, distance, and time, or velocity, acceleration, and time to describe an object, or I can use graphs. Okay. All right. And then the last thing I wanted to show you in here was this just has some examples where free fall it comes into play. All right. So they describe what is free fall for you. And then some phenomena where free fall comes into play. One of them is this idea of weightlessness. Weightlessness. You know, this is like a big talk with all the stuff they had recently about launching the rocket to get to the moon and what have you. And you see, you know, astronauts out in space and they're moving around so freely. But, you know, and we talk about that idea of weightlessness, right? Well, the thing you need to know about weightlessness is that's just a sensation that's produced based on the surroundings of an object, right? It just feels like weightlessness because the object and its surroundings are in free fall. The object is not actually weightless. You know, when you see those astronauts out there, they're not really weightless. They have weight. It's just, it feels like or seems like because of their surroundings, because they're in a craft or a rocket that is free falling. They are free falling and the rocket is free falling, right? So they give an example here, you see. So you're riding in the elevator and somebody cuts the cable and the elevator starts to free fall. Well, the elevator is free falling. You are inside the elevator, so you are also free falling. So you will feel like you're weightless, but you aren't actually weightless. And so here are some, you know, examples. I mentioned the idea of astronauts out in space. They showed a picture down here of the plane. They call it the vomit comet because people ride it just to experience the sensation of weightlessness for a few, you know, seconds. If you've ever been on a Ferris wheel, for example, if it's going around fairly fast, when you're on the way down, for example, you might feel that in the pit of your stomach, right? That's that whole sensation, right? And so none of these folks are actually weightless. It just feels like. So it says here, true or false, an astronaut on a space shuttle feels weightless because there's no gravity in space. There's absolutely false. There is gravity, and we will see when we study gravity deeper later on in this course that there's actually a force of gravity between everything in the universe. But it's because the astronaut is in a shuttle that is free falling, as they say, because she's free falling at the same rate as the craft or shuttle that she's riding in, okay, which is also free fall, okay. We don't need to worry about this. It does illuminate something that when an object is, you know, when it's not experiencing that force on it, it will move in a straight line. For example, and we'll talk about this later on, if an object, you're twirling an object in a circular path and the string pops, is gonna move in a straight line because of the lack of force on it. But we don't want to talk about force too much at this point. That's you know, that's why I don't focus on that example too much. Okay. So though in this extra notes that you can get to right through the announcements, see, I'm in the announcements and I choose the object that says extra resources, click the link, and then it will open a folder that relates to each of the topics. And then you can go into that one-on-one demotion and find all of the examples that I just went through. Okay. So with that, I'm going to stop the share and ask if there are any questions. I know you're on your phone, but hopefully you're able to follow along well enough to where if you have a question, you can put it out there so that I can get it answered for you.
No, I don't really have no questions. I'm gonna go back and look at this video again and once I get home and study a little bit more.
Okay, yeah, and look, feel free to reach out to me if you know, at the point that you have any questions. Remember, because last week that's the one thing I highlighted, that you have to be diligent enough to reach out to me with your questions, because this is a building process, right? If you miss the foundation, then it doesn't make what's coming later any easier. Okay. So with that, I will say thank you for joining me today. Could I get your name just to, you know, it only says iPhone on my screen. I don't exactly know who's here with me. Or how about this? Can you chat and put your name in the chat?
Damien, I'm a
Just
I
type it
can
in.
try.
Try to put your name in the chat. Okay. Or how about, let's do this for me. Okay, Damien, tell me your last name.
Oh, I'm sorry. Joseph.
Say it.
You want me to type it in?
If you can, yeah, go ahead, please. Oh, I see Damien Joseph. Yes, okay, gotcha. Okay, I appreciate that. Well, Mr. Joseph, I really do appreciate you joining me today. I know you have some family events going on right now, but don't hesitate to reach back to me if you have questions.
I sure will.
All right, well, you have a great evening.
Okay, you too, ma'am. All right, thank you.